Hello everyone. So today we will continue with our discussion on the conformations of the cyclohexane. So in the previous class we talked about the different types of conformation that the cyclohexane molecule can have, and we concentrated on two important conformations of the cyclohexane which are free of angle strain, and they were nothing but your boat conformation as well as your chair conformations. Out of them, we compared using Newman projection formula that the chair conformation was kind of more stable than the boat conformation on account of both the fact that chair conformation is kind of a staggered conformation while the boat conformation is kind of an eclipse conformation. Apart from that, in boat conformation, you have interaction between the flat pole hydrogens, which also causes the instability in the boat conformation. So the most common or the most stable conformation in which the cyclohexane molecule exists is your chair conformation. So here in this particular uh, area, you will find that we have the cyclohexane molecule here. Okay, so here I have drawn few cyclohexane molecule in their corresponding chair conformation. So today we are going to look into little bit detail about the bonds that are attached to these carbon atoms, these 6 carbon atoms that are there on the cyclohexane molecule. So if we look at each of these vertices, this is representing a carbon atom. This particular carbon atom is kind of bonded to 2 other carbon atoms, and therefore it has 2 more bonds because each carbon can form approximately 4 bonds. So here you're seeing that it has already formed 2 bonds, so only 2 more bonds are able to be formed at the vertices, and these can be called as the external bonds. Okay, these can be called as the external bonds. Okay, now talking about the external bonds, you will have 2 external bonds that are attached at each of these vertices, because each of the vertices is attached already to the with 2 bonds in the ring. So only left are the 2 extra bonds. Okay, so these external bonds are actually of 2 types. One is your axial bonds, and the other is your equatorial bonds. Axial bonds or the equatorial bonds. Okay, now at each of these vertices you will have 1 axial bond and 1 equatorial bond. Okay, so let us try to draw the axial bonds. So let me use another color for, let you use red color for representing your axial bond. Okay, so axial bond I'll be representing using a red color. These are basically the vertical bonds. These are basically the vertical bonds. So at each of the vertices or at each of these carbon atoms, you will have 1 axial bond. Now axial bonds are vertical bonds. So they are kind of oriented in the vertical direction at each of these vertices. Now, let me start with this particular carbon atom. So at this carbon atom, I'll draw the axial bond in this particular manner. So this would be the axial bond at this particular carbon. Now, why I drew the axial bond in this fashion is because the vertex, this particular vertex is pointed in the upward direction. That's why the axial bond would be in the upward direction. Now coming to this particular carbon atom, the axial bond would be in the downward direction because this vertex is kind of pointing in the downward direction. Similarly, at this point, it would be in the upward direction. At this point in the downward direction, this point again in the upward direction, this point again in the downward direction. So these are the axial bonds. These are the 6 axial bonds that are there at each of these vertices. Okay. Now let us come to the equatorial bond. So equatorial bond, let me represent with the blue color. Okay. So you have the equatorial bonds, they can be called as the slanting bonds. They can be called as slanting bonds. Okay. Now, one axial bond we have already drawn. So obviously another bond that is one other external bond that is there is nothing but the equatorial bond. Now, how to draw the equatorial bond? They are basically slanting lines. Okay, so slanting lines, if you want to draw here, the bond you have to draw here, that should be oriented in parallel to this particular bond. That is the bond that is not the immediate bond, but the next bond. Okay, so at this point, if this you have to draw the equatorial bond at this particular point, then probably you have to orient your equatorial bond in such a way that it is not parallel to the immediate bonds, but the next bonds. Okay, so you will draw the bond something like this. Okay, it would be kind of approximately parallel to not the immediate bonds, but the next bond. Coming to this particular carbon. Okay, here if you want to draw the equatorial bonds, you have to draw it parallel to not the immediate bonds, but the next bond, that is this particular bond. So I will draw this something like this. Okay, now this way also you can see, you have to draw parallel to this particular bond. Another point is, if you come here, you have to draw it not to the immediate, but parallel to this particular point. So you will draw something like this. Coming to this one, not this one, but the next bond. So the parallel bond would be something like this. Now this point, if you want to draw, not the immediate one, that this bond, so it should be something oriented in this particular fashion. Now coming to this bond, again, not this bond, but parallel to this. So you will have the equatorial bond something oriented like this. Okay, so this is how you're going to make the axial and the equatorial bonds. So blue bonds are all equatorial bonds and red ones are all axial bonds. Now let me draw the same thing here as well. Okay, so let me start with the axial bonds. Okay, so as I drew there, the axial bonds would be pointing here in the upward direction, here in the downward direction, here in the upward direction, here in the downward direction, here again in the upward direction, here again in the downward direction. Very simple to understand, because this vertex is pointing in the upward direction, the axial bond would be upward. This vertex is pointing downward, so axial bond would be in the downward. This one again downward, so pointing downwards, upward, upward, downward, downward. Okay, so this is how the bonds are formed in here. Now, let me draw the other bonds. Okay, so the probably the equatorial bonds. Okay, so equatorial bonds, we are representing it with the blue color. Okay, so at each point you will draw the equatorial bond something like this, 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 something like this. Now, I told you it's not the immediate one, parallel to the next one. Okay, so at each of these vertices, I have drawn the corresponding bonds. Okay. So now let us try to draw the what are the atoms. So if you talk about cyclohexane, the atoms attached here are nothing but just a hydrogen. So each of these bonds is attached to hydrogen. So you have hydrogens at each of these external bonds. Okay, so that is what I'm drawing in here. So you have hydrogens formed at each of these hydrogen bonds. Okay, similarly, you will have hydrogens here as well. When it is cyclohexane, it is nothing but C6H12. So it has only the carbons and the hydrogens. The external bonds are nothing but the corresponding hydrogen atoms in the cyclohexane. Now, previous class, I told you that we have these two forms of cyclohexane existing in the solution. So if you ask me the abundance of each of these conformations, they would be equally abundant because there is no difference between these two. They are highly symmetrical structures, okay? And therefore, in solution, there would be a kind of equilibrium between these two conformations of cycloid group. So basically, this kind of movement from this particular conformation to this conformation is called as nothing but ring flipping. This is called as ring flipping, or they are also called as chair flipping. They are also called as chair flipping. Okay, so here when it goes from one structure to another, there is happening a ring flipping. So there is a continuous shift from both shift in both these directions, because there is no energy difference between these two conformations. So you have equal probability of cyclohexane existing in this particular conformation as well as in this particular conformation. Okay, so this is about the simple cyclohexane molecule. Now let me take you to a substituted one. Substituted means one of the hydrogen is substituted with some other atom or group. So in your syllabus, you have to study the conformations for methyl cyclohexane. Okay, so methyl cyclohexane means it is nothing but your cyclohexane ring attached to a methyl group. So that means one of the hydrogens can be substituted with the methyl group. So let me initially draw the axial and the equatorial bonds first quickly. Then we will try to draw the substituted forms. So here I have drawn at each bond. First I'm drawing the axial bonds. On both these conformation, probably I'll draw the structures. Now let me draw the equatorial bonds with the blue bonds. Okay, so you have here the equatorial bonds, here again the equatorial bonds, here again the equatorial bonds, here again the equatorial bonds, equatorial bond, equatorial bond. So after a period of time, you would be able to quickly draw these bonds very simply, like I'm doing right now. For me, it is very simple. I don't have to check whether it's parallel or not. It's just an orientation I have to understand, then I can quickly draw them. Okay, now I'll be putting my substituents here. Okay, so as I told you, one of the carbon, one of the hydrogen is substituted now with the methyl, one of the hydrogen is substituted with the methyl group. So accordingly, you will have anywhere you can attach. So suppose I'll start with here, one of the axial hydrogen I have replaced with the methyl group. But, so this is your methyl cyclohexane. So that means only one hydrogen has been substituted with the methyl group. Rest of them are just the hydrogen. So let me complete the structure. So you have the hydrogens here, hydrogen here, hydrogen here. Everything is hydrogen except one of the hydrogen being replaced by the. Okay. Now what is happening is ring flipping happens. So ring flipping means this particular part of the chair goes down, this particular part of the chair goes up. That is what is happening here. Okay. So the this particular part, suppose I'll number them 1, and this is 2, 3, 4, 5, and 6. Then first carbon has now come down. Okay, then you have 2, 3, fourth carbon has gone up. So you have 4, 5, and 6. Okay, so this is what is happening. Ring flipping means the chair head and chair leg has been flipped in these structures. So now when so in this particular conformation, the methyl group is attached to the first carbon, okay, and it is attached at the axial position. Now when the ring flipping happens, actually what is happening is that there is a whichever group is axial, when it the ring flipping happens, it becomes equatorial. So in this particular structure, when the ring flipping happened, when this first carbon goes down, methyl group won't be drawn in the axial position, but rather it would be drawn in the equatorial position. Okay, so whenever ring flipping happens, there is an interchange of the axial and the equatorial positions happening. So if a group in one of the chair conformation is axial, when the ring flipping happens, it becomes equatorial. Okay, so once I drew this equatorial structure, rest of just them is just a hydrogens. Okay, because only one of the hydrogen has been substituted. So obviously the rest of them are simply hydrogen molecules. So let me complete them here. So you have hydrogens now being attached. Now, when it was cyclohexane, there was no difference in stability. But when it is substituted with a methyl group, there is a stability difference between the two. Okay. Now, what I would like you to do or think about is try to find out why one of the structure is more stable than the other structure. Try to think in terms of either steric reasons, okay, steric effects, okay. Try to draw the Newman projection formulas, and whether you can get some kind of try to think in both these direction, and try to find out what would be the ultimate reason why one of the form is more stable than the other form. This is the form in which you have the axial methyl group, okay, and in this form you have the equatorial methyl group. Okay, so there is a difference here. Okay, and there is a stability difference. Now, which is more stable? I'll just say right now for you, equatorial is more stable than the axial one. Okay, so if you now draw the equilibrium here, the equilibrium would be something like this. Equilibrium would be more in favor of the equatorial form and less in favor of the axial form. Okay, now please try to find out the answer for this. We will try to discuss them. You can write in the comment section, or you can just talk about it in the live session. Okay, till that, till the next class, have a nice day. Thank you very much.